All right, welcome everyone. In this lesson, we're going to be looking at intervals of concavity. So specifically, we're going to see, for a given function, how do we find the intervals where our function's concave up? How do we find the intervals where our function is concave down? And then we'll also see how to find the points of inflection for our function. All right, so let's start with how do we find the intervals of concavity? Well, we know, we've seen this before, that the shape of our function, the concavity of our function, is somehow related to this second derivative, its second derivative. And we've seen this idea before, but let's review over it. For an interval from a to b, if the second derivative is positive on that interval, so greater than 0, then our function is concave up. If the second derivative is negative on that interval, then our function is concave down. So just to shorthand for this, if the second derivative is positive, then our original function is concave up. And a lot of times throughout this, we'll be abbreviating concave up CU. And then our second derivative, if it's negative, then the original function is concave down, which we'll abbreviate, for the most part, CD. All right, so it comes down then, figuring out the intervals of concavity really come down to figuring out the intervals where the second derivative is positive and negative. And so how we're going to approach this is very similar to what we did for intervals of increase-decrease. So let's read through the kind of steps that we're going to go through. So first step will be to calculate the second derivative. If we want the sign of f double prime, well, we first need to know, well, what is f double prime? So we got to calculate it. The next thing is we need to figure out where the second derivative is either 0 or where it's undefined. And those are the places where it can actually change signs. So that's kind of one important thing to note here. You know, why are we interested in these places where f double prime is 0 or where f double prime is undefined? Well, that's where it can really switch signs. So we're interested, you know, how do you go from positive to negative? Well, you either go through 0 or you jump over it and you're undefined. So we need to know if we're interested in where f double prime is positive, negative, well, we need to know where it's 0. That might be a place where it switches signs, or we need to know where it's undefined. And then we use that information then to create a sign chart, and then, you know, essentially then we'll fill out the sign chart. We'll determine the sign of f double prime for each interval. So these places where f double prime is 0 and f double prime does not exist, these are important for our consideration. And we're just going to call them, just a special name over here, we're going to call these the possible inflection numbers. So it's the number x equals c is a possible inflection number of our function, provided either the second derivative at c is 0 or the second derivative at c is undefined. So we're just a little terminology here. And like we said, as you look over this process, the process here for finding the intervals of concavity is going to feel very similar. And the only difference is for intervals of increase-decrease, what did we use? We used f prime. So that's really the only distinction here, is this is a very similar process to our intervals for increase, decrease. And the only difference is which derivative we're using. So for increase, decrease, we're using f prime, and for concave up, concave down, we're using f double prime. So if you can kind of remember this process, we're just repeating the same thing for the second derivative. So it's kind of nice. Okay, so with that in mind, we defined these possible inflection numbers, and the terminology here might be a little kind of ambiguous. Possible, what does that mean? Well, we don't necessarily have an inflection point when the second derivative is 0. We don't necessarily have an inflection point when the second derivative is undefined. There's a little bit more that we need. And so we're going to define an inflection number as it's a number x equals c. There's a couple things here. It's in the domain of our function f. And f double prime has to switch signs there. So these inflection numbers, there's a little bit more going on. It needs to be in the domain of our function. Our second derivative has to switch signs there. And either the second derivative is 0 or the second derivative does not exist. So our possible inflection numbers, what were they? The only requirement there was that either f double prime was equal to 0 or f double prime did not exist at c. So for an inflection number, these requirements are still going to hold, but there's a little bit more we need to check. So we also need to check two things. One, the number has to be in the domain of our original function. So our function has to be defined there. And the second thing is that f double prime has to switch signs. So it has to either go from positive to negative or negative to positive. So these are kind of two things we have to check. We're going to find our possible inflection numbers. That's either where the second derivative is 0 or undefined. But then once we have those, then we're going to go through and double check these extra conditions here to see if it's an actual inflection number. And so if it is an inflection number, well, that means our graph has an inflection point there. And so how do we find the inflection points for our function? There's a little bit more we're going to do. So kind of just going back here to our original, how do we find the intervals of concave up, concave down? We're going to do these 4 steps. And then there's really not too much more work then to find the inflection points. So step 5 is to determine the inflection numbers of f. We already have our possible inflection numbers from before. That's where our second derivative is 0 or undefined. So step 5 is really just going to be to check these 2 extra conditions here. And then once we're certain that we actually do have an inflection number, then the last step, step 6, will be to just figure out, well, what's the actual coordinates of our point? What is the y coordinate? We already have our x coordinate. The last thing there is to find the y coordinate for the inflection point. So essentially what we're doing in step 5 here, we're finding the x coordinates. And then in step 6, we're finding the y coordinates, and we put it all together to nice package it up into an actual point. And so how we're actually going to figure out the y coordinate, this is where we plug into just the original function. So we're going to take our inflection number. We'll take our inflection numbers, and we'll just plug them into the original function f of x. And that's going to give us the y coordinate. Okay. Let's try a few examples. That's what we're going to see next, is just kind of going through the process here, and we'll see how this all kind of works out. So we'll see you there.